So what we have here is we have a truss with two forces pushing on it and it being pinned to the ground by two pin connections at point A and point B. And so what we need to solve for is the forces in each member of the beam and say whether they're in tension or compression. And that's what we're going to solve for in this video. If you find it helpful, hit that like button and don't forget to subscribe. So the first thing we want to do is we want to set up a free body diagram where our X and Y directions are like this, and then we have our truss something like that. We have our two forces going along this, where this is 900 newtons and this one is 600 newtons. And we want to replace our supports with support reactions, and so we will draw this as B sub y and B sub x. And normally I would write A in its components, but in this problem, to make it work, we need to draw A not in its components. So we will label it like this. So it is not split up into its components so that we can solve for all of the reaction forces. And I found that if your support reactions, if their components are in line with each other, such as in this case, the X component of A and the X component of B would be along the same line, then you cannot solve for all of your support reactions without going through the rest of the problem, and it makes it a lot more difficult. But splitting up into this way, we can use a little bit of trig to solve for the rest of this problem. And so another thing we're going to want to draw here is that this angle we will call theta, and it is the same as this angle and this angle. And if we say that the tangent of theta equals the opposite over the adjacent of that angle, that will be this opposite is going to be 3 meters here, or 4 meters, and the adjacent is going to be 3 meters. And so if we take the arctangent of both sides, we'll get that theta equals the arctangent of 4 thirds. And you put that into your calculator, you get that that equals about 53.13 degrees. And so we're going to write this over to here to the side, that theta equals 53.13 degrees. And so setting up our free body diagram is the first step in solving for the internal forces of these members using the method of joints. And so if you want all those, they are down in the description. I have put the steps for solving for the internal forces of a truss using the method of joints. You can see that down there. But the second step, you would go and solve for these reaction forces. And so what we're going to do is we are going to sum moments about a point, and I'm going to choose point D because reaction force A and reaction force B sub y are going to pass through that point D and it will eliminate them. And so we only have B sub x left. And so we sum moments about point D is going to be equal to 0 because the truss is in equilibrium. We are going to say counterclockwise is positive rotation, and so B sub x is going to cause counterclockwise rotation, so we will say it's positive, and B sub x multiplied by 8 to get to point D minus 900, which because it's going clockwise rotation and it is 4 meters away, so multiply by 4, and you multiply these together, add it over to the other side, divide by 8, and you end up getting that b sub x equals 450 newtons. And so we label that here on our free body diagram, 450 newtons. Okay, so that is our first one. Now that we've summed moments about point D, and we have b sub x, we can set up an equilibrium equation for the forces in the x direction. So equals 0, and that way we can find out what reaction force A is. And so it is going in the positive x direction. So its x component would be A, and then cosine of theta, which is 53.1 degrees, plus 450 from the x component of B, minus 900 minus 600 for these two forces, and you end up getting that this is negative 1050. You'll add that over to this side and then divide it by a cosine of 53.1 degrees, and you'll end up getting that A equals 1750 newtons. And that we can label up here. And now that we have that, we can sum forces in our y direction, and the y component of this will be A sine of theta, and we have A and we have theta that we can plug in, minus b sub y. You plug those in and you end up getting that this is 1400, and you add it over to the other side and you end up getting that b sub y equals 1400 newtons. We'll label that up here, and now we have solved for all of our reaction forces. And so step 3 would be to go joint by joint using equilibrium equations to solve for the internal forces of these members. And what you'd be looking for is you'd be looking for a joint with at least one known force and only 2 or less unknown forces. And so looking at this, the only joint that only has 2 unknown forces or less would be joint A. It has the forces in this member, which you'd have your x and y components of, and all the rest of them, like joint D, it would have the x and y components of this member, and this member is only in the y direction, so you'd have 3 unknown forces and 1 known force, which would be at 600 newtons. All the rest of these, again, you're end up getting 3 or more forces that are unknown. And that's what makes this problem more difficult and challenging, because we're going to end up having to set aside equations and components to be able to find out what all the internal forces of these members are. But we are going to start off with joint A, and we are going to say we are at joint A so that we can remember, and we are going to draw a free body diagram of that member. And so you have your reaction force here that is 1750 newtons. And so the internal forces of this member would have to be equal magnitude and opposite direction for it to be equilibrium. And so we would know that the forces in member AE, we'll call it AE, is going to be 1750 newtons. And we will label all of our internal forces of the members we find up here to keep track of them. And because the internal forces would be pushing back on this reaction force, it would be in compression because the internal forces are pushing towards the end of the member. So we will say that this is in compression. Okay, so we have the internal forces, but we're going to want to split this into its components. And so the components of this, we will call it AE sub x and AE sub y. And when we set up our equilibrium equations to solve for those, we will start with the x direction. That would equal a, and then for the x component of this, it would be cosine of theta minus the x component of that, which would be a e sub x. Plug these in and you end up getting that this is 1050 newtons. So a e, if you add this over to the other side, sub x equals 1050 newtons. And now we're going to write that over here so that we can keep track of this, because we're going to need it later. And so that's our forces in the x direction. We do the y direction and we will get that the y component of that will be a, this time sine of theta, minus a e sub y. So basically the same thing. You'll add this over and you'll end up getting that this is the same equation that we solved for using the 1400, and so this is also going to be 1400 newtons. And again, we're going to set this aside over here. Okay, so we've solved for everything in this joint, so we're going to move on to another joint. And so again, normally we'd be looking for a joint that only has 2 unknown forces or less, but we looked at all of them, and even solving for this wouldn't make this joint have only 2 unknown forces. And so we're going to look for another joint, and we're going to go joint by joint looking for the joints that has the least amount of unknown forces. And so we're going to go to joint C. So we draw the free body diagram. It'll look something like that. This one will be from C to D, so we'll call it CD, and this one's from B to C, so we'll call it BC, and this one is going from C to E, so we'll call it CE. And we have our external force right here, which is 900 newtons. The direction in which we draw these arrows doesn't really matter. One way of doing this is just to assume that it is in tension, that the internal forces of each of these members is in tension, and so if your answer comes out positive, you know that it is in tension. If it comes out in negative, it will be in compression. And so we could do that, or we can look at this, and I can look at this and see that this is pushing this way, and so these members are going to be pushing back on it, so they're going to be in compression. These 2 members are going to be stretched out, so they're going to be in tension. These 2 are less clear, but I know that this one is in tension and this one is in compression from having already done this problem, and so I'm going to draw the arrows as such. So this one is in tension, so its internal forces are going to be pushing towards the center of the beam, and so we'll draw it like that. This one as well, and this one is in compression, so it's pushing towards the ends. And so if we set up our equilibrium equations, we're going to find that sum of the forces in the x direction equals 0, and you have your force in CE minus 900. You add this over to the other side and you get that CE equals 900 newtons. Okay, so we found the internal force of that member, and so CE equals 900 newtons. And we found that it was in compression. And if we go to the forces in the y direction, we will find that these 2 are the only forces in the y direction, and so you have that CD minus BC equals 0. Add this over to the other side, and that will just tell you that they're equal. CD equals BC. Okay, so this doesn't really help us solve for these two forces in those members, but we'll end up needing this later, and so we're going to write it over here. Okay, so that's all that we can find in this joint. We're going to move on to joint D now, where we have our free body diagram, our external force, that is 600 newtons, and you have your internal forces on this one. We said that it was going to be in tension, so it is going to be something like that. And this one we said is in, this one is in compression, and this one is in tension. So we're going to draw our arrows like that. We are going to call this again CD, and this one is DE sub X and DE sub Y. We set up our equilibrium equations for the X direction. Sum of the forces in the X direction equals 0, and you have that DEX minus 600. Those are the only forces in the X direction, and they equal 0, so add that over to the other side, and you get that DEX equals 600 newtons. So that's just the X component of the force in that member. So that can't quite go up here, so we're going to set it aside here, and we'll use that later. Now if we sum forces in the Y direction, we will find that DEY minus CD equals 0. So add that over to the other side, so you get that CD equals DEY. And so that's another equation that we'll need to use later. But if we look over here at what we have already, we have that CD equals BC, and here is CD is equal to DE. So we know that all three of these variables are equal. So we'll just add that onto here. Okay, so that's everything at that joint. We're going to go to joint E now, and our free body diagram will look something like this. And remember that this is member AE, and we found its components, and it was in compression, so we'll draw our arrows going towards the end of the beam, and this one was 1050 newtons, and this one's 1400 newtons, and we found that this member, which is CE, was 900 newtons. It was also in compression, so we'll draw it going towards the end of the beam, 900 newtons. This member, we were just at DE. It is in compression, so we'll draw its arrows going towards the end of the beam as well. And we found that our DE sub X was 600 newtons, so we'll label that there. And we didn't find any more than this for DE sub Y. We'll draw that. This one, this member, looking at it, you can tell that it's in tension. If you don't know, you can just say it's in tension. And if it comes out positive, it is in tension. If it comes out negative, it's in compression. But we'll draw the arrows like this. We'll label it B E sub X and BE sub Y. Okay, so these are all the forces acting on that joint. If we sum forces in the X direction, we will find that this one, 1050 minus 600 minus 900 minus or plus BE sub Y, those are all the forces in the X direction. 1050 minus 600 minus 900 is negative 450. You add that over to this side, and you get that B EY equals 450 newtons. And so we will put this over here, and I labeled this wrong. This is actually BE sub X, not BE sub Y. But that is our forces in the X direction. Going to our forces in the Y direction, you get that you have your 1400 plus or minus, because these two are your only other Y forces. So minus D E sub Y minus B E sub Y. And so you'll add these over to the other side and you get that D E sub Y plus B E sub Y equals 1,400. Okay, so this is another equation that doesn't quite get us to solving for these forces, but it's an equation that we'll set aside over here. And so that's all for this joint. Going on to joint B, which is our last joint that we haven't looked at. So its three-body diagram looks something like this. And we have our reaction forces right here, which we solved for was 1400 in the Y direction and 450 newtons in the X direction. And so here we have our member BC, and we said that it was in tension, so we'll draw our arrows going towards the center of the beam, BC. And we have this one, we said that it was also in tension, and we'll call it BE sub Y and BE sub X. And we already solved for BE sub X, remember? It was 450 newtons, and that makes sense because that and the reaction force are the only forces in the X direction. So they need to be equal in magnitude and opposite in direction. And so what we have, if we sum forces in the Y direction, we get that BC plus BEY minus 1400. You add this over to the other side and you end up getting that BC plus BEY equals 1,400. And you'll notice that this is very similar to the equation we got at the last joint, where you have 1400 and BEY. The only difference is BC and DEY. But remember, in this equation, we know that BC and DEY are equal. So these two equations are the exact same. And so they don't get us anywhere, because now we end up with two equations with three unknowns, so we can't solve for all three unknowns. So what we have to do now is we have to use some trig to solve for BE sub Y. And then the rest of the forces will come after that, because we'll have a value to plug into this, and that will help us solve for DEY, and that will get us the rest of these. And so we'll notice here that we have a triangle formed by this member, and its internal force we are going to call BE. And so if we draw this triangle here, where this side is BE, we have the X component of this, which is BE sub X, which is 450, and we don't have its Y component, but we do have the angle here that it is theta. Remember that we solved for it here. It's the same angle. And so we know that the cosine of theta, which is 53.1 degrees, equals the side adjacent, which is 450, divided by BE. You multiply BE over and divide cosine of 53.1 degrees over to this side, and you end up getting that BE is 450 divided by the cosine of 53.1 degrees. And so BE equals 750 newtons. Okay, so that gives us the force in that member, BE, and we found that it was in tension. The forces are going towards the center of the member, and so we'll label that it is in tension. But we need to find BE sub y. So the way you'll do that is similarly the sine of 53.1 degrees equals BE sub y divided by BE, which is 750 newtons. And so you will multiply 750 over to this side, and you'll end up getting that BE sub y equals 600 newtons. And so we will use that to plug that into that equation to solve for everything else that we need. So DE sub y plus BE sub y, which is 600 newtons, equals 1,400. Subtract that over to the other side, you get that DE sub y equals 800 newtons. Okay, so that's just the y component of that force. But you have here that in this equation it says that DEY sub y is equal to CD and BC. So that gives us that these two forces in these two members are 800 newtons, and we will label that up here. And so the last one we need to solve for is DE. And so again, we're going to use our triangle to solve for that. And basically what we're doing here is we're using vector addition, where each of these sides of the triangle is a vector. This side, the hypotenuse, being the force in this member DE. And we said that it was in compression, so we'll draw it going towards the end of the beam. And then we have its components, the x component, or the y component and the x component. So you have your y component, which is 800 newtons, which we'll just leave right there, and our x component, remember we wrote over here that DE sub x is 600 newtons. And so if you want to find this side, which is DE, you'd use the Pythagorean theorem, and you'd get that DE equals the square root of 800 squared plus 600 squared, and that equals 1,000 newtons, which is our force in member DE. And that is the last one we're solving for, and remember we said it was in compression. Alright guys, so that's how you use the method of joints to find the forces in the members and say whether they are in tension or compression. And remember that I put all of these steps for using the method of joints down in the description. You can check that out. I hope you found this video helpful. If you did, hit that like button. If you have any questions or suggestions, you can leave them down in the comments and I will respond to them. And don't forget to subscribe.